Assalamu alaikum everyone. So, so we are going to start chapter 5 today, and in this chapter you will be having the piping design network. So we will do some analysis of piping network, and we will see that how to find some unknown quantities in the complex network. So here we have this piping network, and we can see that there are some series and parallel pipe connections here. So as far as the series piping network analysis is concerned, we have already seen it even before this course, and in this course also in chapter 3 and 4. So in this chapter we will be doing the series and piping both, and then the piping network as well. So here, as you can see, the piping network, that your pump is supplying the liquid to this network. So this is one of the inlet to the network, and these are the exits of the network. This is, and this is, and similarly this one also, and these are the inlets. Basically this is inlet, and this is inlet, and this is inlet. And so in this network we see that there are kind of loops also, and which is a common in most of the networks, because we want to facilitate and we want to minimize the losses. And so we will be doing in this chapter basically the analysis of this. So the piping network problem can be solved through the paperwork, handwork, and through some softwares. So these are some of the softwares like the EPANET. This is one of the freely available downloadable code, and it's very easy and simple to learn. Then we have this Pipeflow Expert. This is a little bit more advanced and more features and more user friendly. And then we have some other uh, solvers also. So basically there are, because the piping network doesn't involve too many equations, so there are simple algorithm behind, and that can be used to solve the network problems. So as we know that there can be series connections like this one, and there can be parallel connection like this one, and there can be a loop of the pipes like this is one loop. So we know that how to do with that. Basically, like if you are here, from here to here this is one pipe, and then from here there are two connections in the loop. This is one connection and then another connection. So this thing we already discussed, that the pressure drop in these two pipes has to be same, and then any one of that will be taken for the net pressure drop or net head loss. So this head loss here, and any one of these two, and then this one, and then this one, so make it the total head loss. And the flow is bifurcated here and here, and then it is again joined. So these things we need to keep in mind, that whenever we have these parallel connections, then how we are going to do with them. So there are certain principles that we need to apply here. That one of the principle is that the continuity equation for the entire network. So the mass flow rate, whatever is the in, the summation of in, that should be equal to the mass flow rate, which is summation of the outlets. So this one is going in, and this one is going in, and these two are in, and this one also, and this is going out, and this is here going out, and this is here going out. So when we take the summation of uh, the, the mass which is going in, and remember that here it is basically the incompressible flow which we are talking about, basically the all liquid flows. So unless it is stated that the flow is compressible, most of the time, almost all like liquid flows, we consider that it is incompressible flow. But there are some situations it can be compressible, but those situations are very rare. So it is incompressible, and for that reason, like the mass flow rate in equals to the mass flow rate out. So the density remains constant. So this is in and this is out. So density cancelled, so basically this summation q in becomes summation q out. So mm, so here it is, come back to the pen, here this is, so which is like the summation q in equals to the summation q out. So here we take the summation q in, so that becomes the sum of these quantities, that is qa qf. So the qa and the qf and the qg, and this is the summation q out, which is qb, qd and qh. So this is called the continuity for the system. And then we have the continuity for each node. For example, this is one node and this is another node. So this is node A, this is node B, and this is node C, and this is node D, and so on. So when we apply the continuity at node A, so the whatever is the number of inlets, so the summation q in equals to the summation q out. So at this node there is only one in, which is qa, and here we have the q3 and q4 as outlet. So this is the continuity at node A. Similarly, we can write the continuity at node B. So here this 4 is going towards the node, so this is, and this is going out, and this is going out. So the Q4 equals to QB plus Q1. And for node C, this one is going in, which is Q1, and this is going out, which is Q5. And here this is going up like this, so going into the node, so this is Q2. So basically the Q1 plus Q2 equals to Q5. So Q1 plus Q2 equals to Q5. So this we call the continuity at each node. So we need to write the continuity at all nodes when we are solving the system. So when we have these two connections which are very much close to each other, so we can ignore this and we can consider that this is entire one point, so that can be point E. So if you want to write the continuity at point E, then the Q3, this is going in Q3, and then Q10 is also going towards E plus Q10, and the Q7 and Q2 are going out, so which is Q7 plus Q2. So these two are going out. So this is the continuity at point E. So now we want to understand this, and we want to do the analysis for the losses, head loss and pressure loss and other things. So we can write the modified continuity equation. So modified Bernoulli's equation. So when you write the modified Bernoulli's equation, then you have to adopt that what are your section of inlet and section where you are applying the Bernoulli equation. So let's see one by one for each pipe element. Like this is the pipe element 1 from B to C, and then from C to E, this is pipe element 2, and then from E to A, this is pipe element 3, and from A to B, this is pipe element 4. So if you want to write the modified Bernoulli's equation or energy equation for the pipe element, that is pipe BC, and then for the time being just ignore the minor losses here. So from pipe 1, for pipe 1 from B to C, we are writing the equation, and then that is that the pressure term, kinetic energy term, and the potential term. So this is at point B, and which is equal to the pressure term, kinetic term and potential term at point B, and then the friction losses in this section and the minor losses in this section. So for the time being, to simplify the procedure, so we are ignoring the minor losses for this time being, but the same procedure can be adopted with the minor loss as well. So when you ignore for the time being the minor losses, and here we know that the velocity just at the inlet of section 1, this line number 1, and just at the exit of the line number 1 will be same, because the cross section is same by the principle of continuity, like the QB that is going to the towards A is equals to the QC for line number 1 we are talking about. So and the mass B for line number 1 equals to the mass flow rate C for line number 1, and then this is multiplied by the density. So the density will be cancelled out, so the flow rate will be same. The flow rate means that the cross section area of the pipe and the diameter, that is pi by 4 d square, this is the cross section, and the velocity at B, and then the pi by 4 d square and the cross velocity at C. So basically this is same, and by this step we can conclude that this is also same. So the velocity term would be cancelled out. So the velocity terms are cancelled out, and the line is laid down horizontally, so this is cancelled out. So these two terms are left on the left hand side. On the right hand side we ignore the minor loss term, so we have only the friction loss term on the right hand side. So which can be written like this. So now we have this thing, delta P dc equals to F1 L1 over d1 rho v1 square over 2. So this is basically the pressure drop in this line. Okay. Similar way, if we go on, then we can find the pressure drop in several other lines also, like from this line to this line, and from this line to this line, and from this line to this line, right? So we can calculate that, let's say from C to E, as you know, like we are considering this as single point E. So C to E, so we can write the delta P C to E, and similarly we can write E to A and then A to B. So here we know that this is velocity, which is q1 over a1, and which can be written for q1 over pi d1 square. So when we have this delta p bc, which is basically from the previous slide, delta p bc, which was f1, which was like here f1 l1 over d1 v1 square over 2g. So this is f1 l1 over d1, then the v1 square over 2g. So the v1, you will substitute this value, so that will be basically 16 q square, 16 q square over pi square, and d1 to the power 4. So this will be your v square, right? And then this you will substitute here, so you will get basically this expression. And from this expression you can basically break them into two parts. This is one part, this is second part. So this one part, first part, we are calling it C1. So our C1 is equals to 8 rho L1 over pi square d1 to the power 5. This is nothing, d1 to the power 5 here. This is our C1. So basically the pressure drop from B to C we can represent in this form. And similarly, any other pressure like from C to E we can represent in this form, and from E to A we can represent in this form, and from A to B we can represent in this form. So here you need to take care of the signs, these signs, right? So these two signs depends upon the flow direction and the loop direction. So here you have to understand that we are going to solve this pipe network, so we have to take care of the signs. So for the sign is that my flow direction is in this direction in the line, and the flow direction is in this direction, so which is this direction in this line, and here my flow direction is this way, and here my flow direction is this way. So there is one is the flow direction which in the lines, and then we can assign a loop direction. So that can be clockwise or that can be anti-clockwise. This is our choice. So here we are choosing that the loop direction is clockwise. So this is loop 1, this is loop 2, this is loop 3, and the loop direction is clockwise. So here we can see that some of the flow directions are along the loop direction and some of the flow direction are opposite, like this. The flow direction in line number 2 is counter to the rotation, counter to the loop direction. The flow direction in this 3 is also counter to the loop direction, and here this is in the direction of the loop. So when we calculate the pressure and when we see, then this we will consider as positive because this is in the direction of the loop. And when we write the pressure delta P CE, this we will take it as negative because this is counter to the flow direction. So, and then when we complete the cycle, when we complete the loop, then all the pressure sums, we will put them equal to 0. So this I will explain you later on that why is it 0. So basically delta P BC, and then because the other is minus, so this is will be taken like minus delta, because this is opposite direction, so this is delta P, that is CE, and then this is again opposite, so this is minus delta P EA, and then plus delta P AB, so this is all equal to 0. So this we will talk later on. So here we see that this pressure we are considering as positive, and this pressure, because of the direction opposite to the loop, we are considering as negative. This is also we are considering negative, and this is positive, and the summation we are making it 0, right? So when we are writing the pressure, the summation of the 0, but when we are considering the sign, when we are substituting the value, then the value substitution should be as per the direction consideration. So this is going to be 0, like that. Now we will talk about this principle, that why the summation is 0. So that we will talk in our next video. So here the thing is that for any loop, the summation of the pressure is 0, but it should be substituted with sign. And the sign convention is that if the flow direction is along the direction of the loop, we will consider that it is positive pressure drop, and if the flow direction is opposite to the loop direction, we will consider it as negative pressure drop. Okay, and then summation is 0. Thank you very much.